Hi all, hi again. Hope everybody is safe at home without being critically affected by this virus spread. Alright, so last time we discussed about AC circuit analysis and how we learned how we can use the knowledge that we gathered in analyzing DC circuits to analyze AC circuits as well. So there we saw that in the place of resistors we'll have to use impedances, and the whole analysis is in the complex number domain. So today we will look at the power in AC circuits. If it for an example, if you think of the household, there are many devices connected to the national grid, and when it comes to the grid, there are many houses, many factories and things like that are connected. So we have to think about the power usage of the devices in order to consider or in order to find out the requirements of power generation. So the reference is chapter 17 of the reference book. Let's look at. So now in the case of DC, we had constant voltage and constant current. So the power was P is equal to VI. But now we know that in when it comes to AC, the input waveform, that is the voltage or the current waveform, is not a constant value, but it varies with time. It's continuously varying with time in a sinusoidal pattern. So now we will have to, instead of talking about the power, we have to talk about the instantaneous power, the power for that given moment. So which is referred to as P is equal to VI. So that V and I are the time domain functions, that is time variable functions that we discussed earlier, the voltage as well as the current. So in this case, in this diagram, as you can see here, voltage varies like this and current varies like this. So that these waveforms are the functions of the mathematical functions of those waveforms are what you can get in here. So at a given point, as you can see in this diagram, the power also varies. So you have to actually multiply the voltage value and the current value when you get the power value calculators. As you can see here, there are certain parts where the power is positive, meaning that power goes into the load, and there are certain parts where the power is negative, meaning that the power comes out of the load, or that is load to the source. So that is what you actually can see in the case of this power calculation called the power curve, right? So power may flow into the load as well as it may come out of the load at times in general, right? So then we have actually several types of power that we had to discuss in this case. As you can see, now this is completely different from what we saw with the DC, because in the case of DC, it is a constant voltage and a constant current. So power was always going into the load, but now it is not the case. So we will take into consideration several parameters that we talk in, or that we consider in power. So the first is the active power. Active power is actually the average of this power waveform average, which is net amount that has actually gone into the load. This is also referred to as the real power, because it is the real component or real amount of power, active power, or else average power. All these names are used interchangeably to refer to the same value, which is the average of the power of a general AC load. So the value is represented by the capital letter P, the active power. Now then the other component of power is the reactive power, there is certain amount of power that goes into the load and comes back fully. That particular part of power is referred to as the reactive power, right? So inductors and capacitors do have reactive power, and the average of that, because this amount of this portion of power goes into the load and comes out fully, so therefore the average of that reactive power is 0, and the average reactive power is represented by the letter capital Q, right? So as you can see, it is going into the load at some time and coming out of the load at another time. There is no use of that component of power to the load. There is nothing we could do with that power because it goes in but it comes out in another time. However, as you can also see, you need to generate that amount of power and you need to give that amount of power, because at some point it is going in, right? So at some point it is going in, meaning that you need to create that power as well. Although it is at another point it is coming back. Now if you actually look at this, you need to generate this amount of power, although at a certain other point part of it is coming back. So therefore, now this is the full power, which is actually the later on we will get to know that what you mean actually by this total power, but this is actually combination of both active and reactive powers. And so part of it is the reactive power which is fully coming out, but the point is that although it is coming out at a given point at certain time, we have to produce that power because it is supposed to go in at a different at an earlier time or different time. So we need to we can't actually leave aside, or we can't actually forget about the apparent power, although it doesn't do anything meaningful or any work. We can't get any work out of that component of power because at some other point it has to come out, right? So extra current will have to flow through the circuit, and extra current, extra power will have to be generated by the generation side to satisfy, also to allow this amount of power to go into the load. Now let's look at, for each component, the analytical side of it. Each components, what sort of a power is there. So power to a resistive load. So we know that from the basics of that is the two lectures back we talk about the basics. So current and the voltage for a resistor is in line or in phase. So if you take current as Im sin omega t, voltage is Vm sin omega t. So if you find the power that is P is equal to Vi, you multiply these two values, so you get Im Vm sin squared omega t, right? So sin squared omega t. Now you take the average of it. That average becomes Vm Im over 2, which is actually Vrms into Irms. So for and you can see that here the average of this part is becomes 0, so it is actually Vrms into Irms, right? And from this graph you can see what we do here in this graph, in creating this graph, is you basically multiply each point, or basically you plot this waveform. So because it is 1 minus cos omega t, the whole thing is in the cos 2 omega t. The total waveform, this waveform is actually in the positive direction, because the maximum value that the cos omega t can go is plus 1. So 1 minus 1 is 0, right? And the minimum value is, if it is negative, it is minus 1. In that case it is twice the value of this. So it actually goes to twice of this amount, that is actually VMIM. However, as you can see from this equation as well as in this diagram, the total power is positive, meaning that the resistor has only active power component, right? There is no power component that is returning, meaning that reactive power doesn't exist in the resistor. So it actually can generate heat, or energy can be transferred. Then if you think of inductive load, for an inductor we know that voltage is leading by 90 degrees. So if you take current as the reference, and current equals to Em sin omega t, voltage is Vm sin omega t plus 90 degrees. Now if you multiply these two, you get this equation Vm Im sin omega t plus 90 degrees into sin omega t, which is actually sin 2 omega t divided by 2. So that 2, if you take in under these 2 as root 2 into root 2, this is then Vm over root 2, Vim over root 2. So Vm over root 2 is Vrms, Im over root 2 is Irms. So it is V into I, Vrms Irms sin 2 omega t. So that is because sin omega t plus 90 is cos omega t plus omega sin omega t, that is sin 2 omega t by 2, right? So therefore, as you can see here, the average of this is 0, and that does mean that this is completely reactive power, fully reactive. As you can see in this waveform as well, this area under this part as well as area under this part are equal to each other, meaning that the average is 0, right? So now this is reactive power, fully reactive power. The product, this V into I product, is referred to as the reactive power. To represent that, we don't use the unit watts in here, but we use the unit VAR. So VA is to represent actually the voltage amperes, volt amperes, reactive. So R term is there because we know that this is fully reactive power, right? So there is nothing we can do with it, but we'll have to produce that because at certain point it has to go in, right? So we can actually use other terms as well, using the Ohm's law relationship for the voltage and the current. So I squared XL, V squared over, all these things can be used, but this we have to keep in mind that this is reactive power. That is why this last letter R is there, right? Right. So the next component is capacitive loads. For a capacitor, we know that the voltage is lagging by 90 degrees. So again, if we take current as reference, voltage is sin omega t minus 90 degrees, right? Now this will give us minus sin 2 omega t. Again, that by 2 term is there, so that divide by 2 is taken as divide by root 2 in here and root 2 in here. So with that we get the relationship for PC as minus VI, V RMS I RMS sin 2 omega t. It is similar, except that it is exactly opposite direction, right? As you can see, inverted. So again, this is reactive power. So VAR, right? VI is reactive power, volt ampere reactive. Now as you can see here, this is negative and this is positive. So therefore what we do is we consider the inductive reactive power as positive and capacitive reactive power as negative. But still you can hold these equations, that is Q is equal to I squared C and V squared over XC, I squared XC or V squared over XC can be used. Right, so if you take these examples, right, For each circuit, I hope you have actually understood the concept behind the active power or real power or active power for resistors actually, then reactive power, two types of reactive power, right? That is inductive reactive power and capacitive reactive power, right? One is opposite to the other. We treat inductive reactive power as positive and capacitive reactive power as negative, right? Right. So now, so this example it says for each right. So for the first case, that is the first circuit, that is A. What we have is a resistor, so it's actually average power or real power P is equal to we know the value of R, so we can use V squared over R, right? V squared over R, which is 100 squared over R is 25, which is equal to, I'm going to use the calculator for that calculation, 100 squared divided by 25, which is equal to 100 squared divided by 25, which is 400 watts, right? 400 watts. Now what about for this one, right? Any suggestions? Second circuit, right? So you have an inductor. So what should be the power value? Is it active power? No, right? So active power is for resistors, but here we have an inductor, therefore it's a reactive power Q. Q, and it's for inductor as well. So QL is equal to, again we know the reactance, inductive reactance, and the voltage. So we can use V squared over XL, right? So it's actually I had to correct this. I think it's just V squared over XL, right? So that is what is V squared? Again 100, right? 100 squared divided by XL is 20. So it's, I think, 500, right? Let me check. 100 squared divided by 20 is equal to 500, right? So it's 500 V A R, within brackets we can write inductive, or plus 500 VAR. C, now we have a capacitor, right? So what's the reactance, rather the power? Again reactive power, so QC is V squared over XL, XC, right? So that is 100 squared over 40, which is 250 VAR capacitive, or we can write it as minus 250 VAR, right? So I think we have discussed that here, right? We can use minus sign there, right, for capacitive reactance. Okay, I think you got that point. Let's move on to the next. Okay, the answers are given here, right? And we don't have any p value for the second and the third case. We don't have any q value for the first case, right? Okay, now that is for a single component, right? So we had a resistor, we had a capacitor, and we had an inductor separately or individual. But in a general circuit, you may have combinations of components, series, parallel, whatever it is. Now when it comes to power, irrespective of the connectivity of the components, we can actually treat the power components individually, right? So the total power, total real power in that scenario is the addition of the real power consumptions of individual components. Similarly, the reactive power, as you can see in this equation, the reactive power, the total reactive power is the addition of the reactive power values of each component or all the components. So in that case, now real power, we know that all the real power components are positive. But reactive power components, if it is a capacitor, it is negative, and it, for an inductive, we treat it as a positive reactive power. So therefore, what we can this same equation can be rewritten, taking into consideration that inductive reactive power is positive and capacitive reactive power is negative. We can say total of inductive minus total of capacitive, or simply you treat inductive reactances as positive and capacitive reactive powers as negative, and just add them together, right? You get the total reactive power, right? So this is how you find the total power. Again, now when you find the total power, we have to treat the active power separate and reactive power separate. Now let's take an example. In this case, we have an RL circuit. Current is 5 amperes. So we know that for this resistor we have real power, which is I squared R, which is equal to 75 watts. And for this inductor separately, it's alone, right? Inductor alone, we have QL. QL is equal to, or Q is equal to QL, which is I squared XL. XL is 4, so it is 5 squared 4, which is 100 VAR inductive. So we can now model this circuit in terms of power, as there is something that consumes 75 watts of real power and 100 VAR of reactive power, right? Now another example where you have a parallel circuit, still it's the same, where you have this resistor, again real power, we can calculate using V squared over R, because V is known, right? So with that you can actually get P is equal to 80 watts, and for Q, reactive power component, which is this one, V squared over XC, which is 20 VAR capacitive. Now, so the same circuit can be modeled in terms of power, as there is something that consumes 80 watts of real power and 20 VAR of capacitive reactive power, right? So that's the modeling thing. Okay, now let's find for the circuit in the figure, we want to find PT and QT, right? And we can actually change this to a simplified circuit. So let's take this, let's use tape, right? I would like to use text, yeah, I mean this one here. Okay, so we have actually a resistor here, right? So for the resistor we have let's say P, right? P is equal to we know that it is 20 amperes, so we can write I squared R, which is equal to 20 squared into 3, that is in watts. So 20 squared is 20 squared into 3, so that is 1200, right? 1200 watts. Now let's take individual components, XC, right? So for C1, right, we will say Q1 or QC1, right? So QC1 is equal to, again we know the current, so we can use I squared XC. I squared is 20 squared into 6. This is VAR capacitive, right? So this is equal to, we can say minus, right, because capacitive, that's 20 squared into 6 is 2400 VAR. I took as minus, so I don't have to consider again about, I don't have to have in brackets that it is capacitive or whether it is capacitive or inductive. Now for C2, it is QC2. Because we know the voltage, voltage across these two, we can use V squared over XC2, right? So V squared is 200 squared divided by XC is 10, right? This is VAR, again capacitive, right? Capacitive reactive power. This is equal to 200 squared divided by 10, which is 200 squared divided by how much? 10. It is 4000, right? So minus 4000 VAR. The last is the capacitor, rather inductor. So for L, QL is equal to, again V squared XL, which is 200 squared over 5, which is again, that is VAR inductive. So it is 8000 VAR plus, because it is an inductor. Now PT, right? So PT, total power, is equal to P, because we have only one component that actually consumes real power, which is 1200 watts. 1200 watts. Now QT is the addition of each Q values. So QC1 plus QC2 plus QL. So I'm using that second technique that I was telling you. So this is minus 2400 minus 2400 VAR minus 4000 VAR plus 8000 VAR. So that is equal to, let's use the calculator, right? I don't want you to make any mistake by doing the calculation in your mind, right? So minus 2400 minus 4000 plus 8000, which is 1600 plus. So 1600 VAR, or we can write it as 1600 VAR inductive, because it is positive, right? Now what are they asking? The last part of the question is reduce the circuit into its simplest form. So we know that we have some P, we have some Q, right? So we can model it as a series circuit if you wish, right? Or individual components can also be written, right? Let's see what it is. So that is what they have done, right? So simple form is this, right? They have done the calculations. So 1000 watts, right? 1200 watts. Was it the case for us? I think so, right? We've not done a mistake, I guess. Yeah. Oh, yeah, 1200 watts. Yes. and 2400 VAR capacitive, 4000 VAR capacitive, and 8000 VAR inductive. And yes, as I said earlier, you can simply model it as a series circuit of 1000 watts, because we got PT as 1000 watts and QT as 1600 VAR inductive. So you can just model it as something that consumes 1200 watts, something that consumes 1600 VAR. Now inductive. Now what is the purpose of putting this in series in here? Now note that here we were given the current that goes into the circuit as 20 amperes. So in that case we will have to use a series circuit instead of a parallel circuit. But otherwise there is actually no difference in that. But if the voltage was given, we could have used that as a parallel circuit as well. But here now the current is given, so therefore we have to model it as a series circuit, because we know the current is equal to 20 amperes, that the current is equal to 20 amperes. Okay, right. So now we can calculate what the resistance doesn't change because it's 20 amperes and so on, but we can calculate the value of the inductor of this equivalent circuit, because using this relationship, Q is equal to I squared over X, I squared X. So X is equal to Q over I squared. So Q is equal to 1600 divided by 20 squared. So we get 24 ohms is the equivalent inductor that consumes 1600 VAR. Right? Now I used the word consumes because it is actually need to be generated, but it can't be converted into any other source or any other power energy source, energy type. Okay, now let me explain this in this way. You have a device, don't know what is the composition or what do you have inside, whether there are resistors, capacitors, or whatever it is, you don't know, but you can measure the voltage, can't you? Right? How can you measure it? Maybe using a voltmeter, right? AC voltmeter, you can measure the voltage. Also the current, right? Current that goes into the load. We don't know what are the currents in the branches and things like that. We don't know. Let's say it's a lamp, fan, whatever it is. You can measure still the current using a, what is that? AC current meter, AC ammeter. Now you know the voltage given and the current given. Just multiply those two. That is actually what we see as going into the device, right? Which is the apparent power. Apparent means appear, right? You see that amount of power as going into the device without knowing whether part of it or whether it is reactive power or real power. You don't know, right? So in that case we can say, okay, S is equal to V into I. V is the RMS voltage measured at the input. I is the RMS current measured as going into the load. Two other alternatives can also be used. I squared Z, V squared over Z. Note that this is now not the reactance, because we don't know what is the combination that you have inside the load. So we simply treat that as a general impedance, right? So for kilo, if you want to, in that case we use the symbol VA, volt amperes, again because it is we don't know whether it is a real power or not. We don't use the term watts, right? There can be, if this whole thing is a pure resistor, then this whole thing VI is a watt, right? It is real power, but we don't know. When you look at the device, we don't know whether it is a fully resistive power. Little later on we will consider some of the sources and see whether they are resistive, reactive, inductive, capacitive, whatever it is, right? Little later on. But for the moment there is a load. You just connect it to the power source, and what you can see is the voltage at the input and the current that is drawn by the load. So in that case, it is the apparent power that is delivered to the load. Now for a circuit, we can try to derive a relationship between. Now we have learned about three components. One is real power P, second reactive power Q, third apparent power S. So P, Q, S. Now we will try to build up a relationship between these three. Now for this RL circuit, we can draw the power draw the what is this, the phasor diagram, right? So VR goes that way, VL goes that way, and total voltage V is this, right? Now let's take out the scalar values, right? This is not anymore a phasor diagram now, just a triangle. When it comes to here, you just take the triangle, right? V is equal to I into R, we know that, and L, VL, so VR is equal to IR, VL is equal to IXL. So that is in magnitude, that also we know, right? Now for this is just a triangle, it's not a phasor diagram anymore now. If you multiply all the three sides by the scalar value I, magnitude of the current, still the aspect ratio remains unchanged, right? But size will be increased, but the shape of this triangle will remain still unchanged. So this angle is same, this angle is same, and this is a right angle. Now what is this? Can anyone tell me? Right? That is I squared R. I squared R is the P, right? That is the real power. What about this one? That's I squared XL. I squared XL is XL, inductive. So inductive reactive power, QL. What about this? We just looked at it. VI. VI is the apparent power. So this forms the power triangle, right, for the RL circuit. Right? Now from this you can derive all these relationships. S is equal to P squared over Q squared square root. Then still we can use the complex number domain to represent this. So S, all these are not complex values, but to represent it we can write S is equal to P plus JQ, right? And the angle theta is equal to S, that in the complex number domain can be represented as S angle theta, right? So that angle is the angle in here, which is tan inverse Q over P, right? QL over P. Same thing for this, if it is for a capacitor, if you replace this by a capacitor, the phasor diagram will go downwards. So again you can do the same thing, right? Same process, but the triangular will be like this downwards, and you get this equation. So in that case, if to represent it in the complex number domain, you can use S is equal to P minus QL, because now we treat the Q's as negative values, right? P minus JQC. So this forms the power triangle for a capacitor. Now the power relationship, P is equal to S is equal to P plus Q. We know that this is actually complex number in complex number domain. We represent Q values with respect to this triangle. Again, it's not actually a power triangle, phasor diagram or anything like that, but just to represent this power triangle. It is not actually a phasor diagram or a vector diagram, not like that, but to represent this relationship we can use the complex numbers. So this is on the real axis, so this you can treat as a complex number, this you can treat as a complex number, which is JXL, and this also can be represented as a complex number. So in that case, two complex numbers added to give a complex number result. So S is equal to P plus Q in that case. So P is P angle 0, Q is equal to JQL or JQC. You can add them together to get the resultant um, Q value, like what we did earlier. And so in this case S is equal to VI complex conjugate, I conjugate I star. However, now one thing we have to remember is, although we could add the P components together, Q components together, we can't add the S values, the apparent power values together. So this doesn't, this equation, that is the total apparent power, is not the sum of individual apparent powers. So here, but if you want to find the total apparent power, what you need to do is to add P values. You have to find PT, you have to find QT, draw the power triangle for the total values PT and QT, and find S. So in that case, S is equal to ST is equal to PT plus QT. Right, so now we will look at this example of, wow, it's a very complex diagram as it looks like. However, as you can see, let's take this circuit into zonal and go ahead with the calculations. Right, so we have actually several components in here, so don't have to worry, because what we said was PT, QT can be calculated easy, right? So what does this question says? The P and Q values of a circuit are shown in the figure. Determine the power triangle, determine the magnitude of the current supplied by the source. So once you know the apparent power S, you can use S is equal to VI to find I. So we have to find out S. We know that we can't calculate S. Now here individual components are there, right? So which has, each has S, but as S total is not equal to the sum of individual S's, we have to find PT and QT separately. Let's do that. Can you also do that with me? Right? So PT is equal to, we will take each now the real power value of each component. So we have several devices connected in several ways. So this is 700 watts, 700 watts plus 800 watts here, and this doesn't have any P value, and we have 80 watts only here, and we have 120 watts here, right? So this is equal to this is 200 200 plus 800 is 1700 watts. Let me double check it with the calculator, right? I don't want to make any mistake in here. So 800 plus 80 plus 120, which is 1700, right? Now what about Q? QT, can you give me an answer? QT, you just add individual components. So 1300 is inductive, so that is plus, so 1300 VAR. Now this is capacitive, so it is minus 600 VAR. Then this is capacitive, again minus, so minus 600 VAR. What else? This doesn't have any reactive power, but this has again capacitive, 1200 VAR, so minus 1200 VAR, which gives us how much? I think 700, right? Oh no, 600, 1200, 1100. Let's say. So 1300 minus 600 minus 600 minus 1200, which is minus 1100 VAR, meaning that it is 1100 VAR capacitive, right? So any of these options can be used, or either like this, either or like this, right? So now we are supposed to find draw the power triangle. So we have P. How much is it? Oops, let's enable this feature. 1700. P is 1700. Q is less than that, and it is negative because it is a capacitive, so I'm drawing like this, right? This is Q, and S is here. So P equals PT equals 1700 watts, QT equals 1100 VAR capacitive. Then S. What is S? The size of S as well as theta, right? S is equal to square root of PT squared ST, right? This is ST, total apparent power. ST is PT squared plus QT squared, which is square root of 1700 square plus 1100 square, right? So that is equal to 1700 square plus 1100 square square root equals to 2020 25 approximately 25 VA. Sorry, R is not there, VA, right? Apparent power. Now what is the current? S is equal to, something wrong there, I think the tip is worn. Anyway, let's see. I'll try my best to get something more out of it. So this is equal to S is equal to what? VI. So what is V? V is 120. So S is equal to, previously we calculated, so we want to find I. I is equal to S over V, which is 2025 VA divided by 120 volts, which is 2025 divided by 120 equal to 16.785 amperes, right? Right, so that's that. Let's see if our results are correct. Oops, done a mistake, it seems. Oh, let's see, did I do a mistake? Oh yes, I have done a mistake. That mistake is, this is 100, not 600. So this is 100, so that's 100 means how much is this? Let's do that calculation again, right? That is 1300 minus 600 minus 100 minus 1200, which is 600 actually. So minus 600, so 600 VAR, and this is actually 600. So in that case I think the triangle has to be little different, right? Because 600 into this, it's like something like 1 into 3 or 3, yeah, 1 into 3, right? So this is S, this is 600, right? Now this becomes 600, and in that case this is how much? So 1700 squared plus 600 squared, that square root is 1803, right? So in that case this has to be 1803, 1803. So 1803 divided by 120 is 50, approximately 15 amperes. It's 15.025, right? 15.025. Done. So is that correct now? Yes, it's correct. Now you see, right, you can see that the complexity of this is enormous, right? You have parallel, you have series, you have then something going parallel to that, all, right? However, well, now if you have devices like this, the voltage, current, things like that can change. However, the power holds unchanged, meaning you just can add the real power components together to get the total power, total real power, and you can add the reactive powers together to get the total reactive power here, right? So that is the important point in here. Now from the power triangle, if you just look at this power triangle, right, P is equal to S cos theta, and Q is equal to S sin theta. So that's this, right? Simple relationship, trigonometric relationship. And S is VI, right? V is RMS voltage, I is RMS current at the input, right? So P is equal to VI cos theta, and Q is equal to VI sin theta. So these two are the two equations that we need to know in terms of the power relationships, right? P is always positive, as we already discussed. Q can be positive for what? Q can be positive for inductors, and Q can be negative for capacitors, right? So Q can be positive or negative depending on whether it is a capacitor or an inductor, but P is always positive, right? Now the power factor. Now what is this power factor? Now you have to give, actually, like, input has to be given, which is the apparent power, right? Now, like, okay, now if you take an example, now I'll continue that statement, right? So we have to give an amount of S to the device, but you can get actually worth of P out of it, the real power, right? So that ratio, how much power, how much work that actually we can get from the work given into it, or how much power that we can get as work output compared to the full power that we are giving. That ratio, it's like, let's say you eat a lot but do a less, right? So you are not good at working, but there can be people who eat less but do a lot, so there we are good, right? Such people are good. So likewise, you need to know how much from whatever you are giving is taken as the real power, right? Given as the real power. So that is the power factor, which is the ratio between the real power and the apparent power. Now real power is actually the amount of power that this device can use or work with or convert into any energy source, that like kinetic, maybe in the case of a fan, in the case of a light it is the light output, in the case of a heater it is the heat output, something like that, right? The real power, right? But the apparent power is something that you actually give into it, right? Out of that, some component is useless, that is the reactive power. So this ratio is known as the power factor, right? So power factor is defined as the cos theta, and the power factor angle is theta, right? So this is basically the ratio between the real power and the apparent power. So I took these examples, in the case of let's say a fan, The active power component is what actually makes this moving, and airflow is there, and so on and so forth. Maybe heat is also there, but that is also real power, right? For a fan it is like, for a heater it's actually the heat output, for a light the light output. So that is the real power component, but there can be reactive power components as well, right? That is actually creating the unnecessary amount of work, right? Amount of energy, or rather power, to be given. Now there are three types of power factors by the behavior of power factor: unity, lagging, and leading. For an example, if you don't have inductive components and the power factor is 0, or power factor is 1, the angle is 1, angle is 0, the power factor is 1, meaning that the total power is reactive power, active power. In that case we call it as unity power factor. So in that case P is Vi cos theta. Cos theta is 1, and therefore P will be directly Vi. It's for a resistive load, a heater, immersion heater, hot plate, all those are purely resistive loads. Then in that case it's a we call it as unity power factor. Unity power factor becomes 1. The second is in the case of capacitive, right? For a capacitor, current is leading, so therefore we call it as leading power factor. For an inductor, current is lagging, so therefore we call the power factor is lagging. So lagging power factor, leading power factor. So that does mean inductor has a lagging power factor and a capacitor has a leading power factor. So anyway, if it is an inductive load, that is having a lagging power factor. If it is a capacitive power circuit, it has a leading power factor. So that leading or lagness is based on the current. If the current is leading, we have a leading power factor. Current is lagging, we have a lagging power factor. Now what are the devices that we will have capacitive loads or inductive loads? Definitely, okay, motor has a winding, that means it has an inductive, so it is having an inductor as well as a resistance. So that is sort of an inductive load which has resistive part as well. Capacitive, I actually can't think of sort of a capacitive load as such, but there can be capacitive loads as well. Now we got to know all these power things, active power, reactive power, right, apparent power, and so on and so forth. Now household, you might, most of the time you might see watts, right? An iron, steam iron is in the range of 1200 to 2000 watts. Immersion heaters, even something like that, maybe 1800 watts, 2000 watts, and so on and so forth. But when it comes to industry, instead of marking them as watts, they mark them as volt amperes. The power rating is marked as volt amperes. That is because of this reason. The reason is, now if you mark the wattage, that indicates the real power consumption. But one device, that same device can have an inductive component or a capacitive. In general, most of cases, we'll take some examples little later on. Most of cases it will be inductive component, like motors, fans, blowers, all those stuff are inductive, and resistive part is there. So now as you can see here, apparent power is much larger than the real power. So actually you need 333 amperes will be drawn, RMS will be drawn by the load, not 200. So if you plan it for 200, you will be lost. So you won't be able to handle that current in the wiring, and so on and so forth will be there. All these drawbacks, all those issues would be there if you plan for just the wattage, that is the real power. So you need to plan for the apparent power. Even the wiring has to be supporting that high current, and your supply needs to be supporting that current. You need to generate that current in the by the supply and all. So all these effects are there. So therefore that is why the devices, particularly the industrial devices, are rated as volt amperes, that is the apparent power. If you give in this much of voltage, that is the standard voltage. If it is single phase 230 in Sri Lanka, it may be 3 phase, whatever it is. So it is marking the current. You can calculate the current, total RMS current that will be drawn. But keep in mind, part of it is returning, but you can't just forget about that part. You will have to consider that as well. So that is why the devices are rated as rating is given as volt amperes instead of watts. Now the power factor correction, right? So earlier we saw that we had a non-zero power factor, right? So why do we need the power factor to be corrected, right? Now as you can, okay, this is a good example. I think most of boys, right, know what this means, right? Yeah, is it the case, right? Maybe there are some females as well, some girls as well, who know this better than girls, right? Yeah. Right, anyway, so what is represented in here is, okay, well, when it comes to power, it is not like linear, but this will give you a real meaning, or the meaning, synonym meaning of what we are talking about. Now you pay for the beer glass, right? But you actually have drinkable amount of this, right? So it's like you have the total apparent power, it's full, like you have the total apparent power, but you can use only you can actually get some work from the real power. The apparent power is, I mean, it's actually a waste. You can't use that apparent power to get some work out of it, right? So the next slide shows a comparison between these two. Right, so this actually shows, now we were talking about this power factor thing, and this actually shows if you have more froth and less froth. Anyway, you will have to, let's say, one thing that these boys know, right? What they know very well about this. So you go to the pub and you order beer, right? And what you get is either this or this. What would you prefer? The left hand side or the right hand side? I know your answer is the right hand side, right? So because you have more beer in this case and less froth, you can't actually avoid this, right? In the pub case, or in the bar, you can't actually avoid this. But if you in this second, the left hand side case, you have less beer but more froth. So what we would prefer is the right hand side case, and we will try to do the same thing with the power, right? So more reactive, more active power and less reactive power will actually cause less amount of apparent power, which actually we have to give it to the load, right? So this is what is called as the power factor correction. We will try to bring this to this level, right? Now in that correction case, so here you saw that there is some reactive power, right? So we can remove that if we can remove that reactive power fully, we will have to only supply the active power, right? This case actually is known as the unity power factor correction. That means you cancel out the entire amount of reactive power, so you get only active power remaining, right? How can you do that? Now most of the Before that, before how you see how we can control this, how we can reduce the achieve power factor correction. Now, what about the loads that that are there in the industry? We have what do you have? You have motors, fans, lights. Now, when you consider the lights, the amount of power consumption of the lights is much less compared with the motors, fans, and things like that. So, in that case, most of the loads, now there can be heaters. Heaters are purely resistive, or they consume only active power. So, other than the heavy loads, when you think about the heavy loads, majority of heavy loads, or we can say all of the heavy loads are inductive because they have motors in them. The moment that you have a motor in them, there is a inductance involved. So, they are inductive loads. The net load, therefore, because you knew that earlier, that you can adapt the inductive power, rather reactive power separately, and active power separately. With that knowledge, we can see that the net power total is actually inductive, total load is inductive. So, keeping that in mind, anyway, for domestic users, they actually can't control this apparent power, and they have an generic estimation. The electricity board in here, the utility has a generic estimation of what amount of power factors would be there, and they charge based on a active power formula, based on active power used. But they know that there is certain amount of reactive power that they need to provide. But putting that count into the tariff, the bill, they only charge for they are charging formula only depends on the active power. But when it comes to industry, it is not the case. Industry, they measure the real rather the apparent power and charged for the apparent power instead of the real power. So, in that case, the industrial customer would be charged for the total amount of power that is consumed, not only for the real power. That is not that is only one side. So, therefore they expect the industrial customers to reduce the power factor, or improve the power factor, reduce the inductiveness of the load. And on the other hand, now we are talking about megawatts of power, right? So, the electricity board in Sri Lanka has to generate that excess amount of power if there is heavy inductive components available in the industrial loads. So, they have a ruling saying that if let's say you have a company, you have a factory, power factor has to be controlled at a certain level, maybe 0.85, 0.9 or so. If the power factor is less than that, they charge an extra penalty on the customer, right? They do that because they have to generate that amount of power if that exists, right? So, now we will look at that is the whole reason why we need the power factor to be corrected. One is the customer side, that is the industry customer needs to pay that amount if it is extra, and the generator side, the electricity board, has to generate that, which is more critical than paying that amount, right? So, therefore, we will have to look into power factor correction. So, in this case, we have seen that, okay, this example, we have seen that we had an inductive reactive power of 160 kilovolt ampere reactive. So, if we can replace that with a capacitor, knowing the fact that we just before discussed that the total load is inductive, and we know that inductive reactive power can be cancelled by the capacitive reactive power. So, if you install a capacitor that has the same amount of that is 160 kilovolt ampere reactive of capacitive reactive power, that can 100% cancel out this. So, this is 160 kVAR capacitive. In the load you have 160 kVAR active, inductive. So inductive and capacitive cancels out and will become 0 VAR. So now you will have to provide only the active power. So the current will be 200, I guess. So 200 amperes only, right? So that will give us a very relieved situation. Now this is full power factor correction, right? I mean unity power factor correction, but we may have to correct it to a certain level, not 100%, but maybe to 90%, right? So bring it up to 90%, right? So those things, if you take the same example, if you want the power factor to be corrected to 90%, let's take that example, right? This is what we have, right? If we want the power factor to be corrected to 90%, right? So what is the power factor here? Let's calculate the power factor, right? So the power factor here is okay, S. What is S? S is equal to P squared plus Q squared square root, which is 120 squared plus 160 squared square root, right? kVA. What is this now? 120 squared plus 160 120 squared plus 160 squared square root is 200, right? So this is 200 kVA. So what is the power factor? FP, right? FP is equal to P over S, which is 120 over 200, which is 120 divided by 200 is equal to 0.6, right? So if we want the power factor to be corrected to 0.9 instead of 1, right? 0.9. Earlier what we considered was 1, because in general case we don't expect it to be 100% corrected, because there can be different loads connected at different times and things like that. So therefore, and the cost wise, achieving 100% power factor or unity power factor correction is costlier than achieving up to about 90-95%. So let's take consider the case that we want to achieve 0.9 power factor. So in that case, what we want is, we have P, right? We have Q, right? And we have S. S is something that we don't actually want at this point, right? Well, for the calculations here we need, but we are not too much interested of S, but we are interested of the resultant power factor, that is FP to be 0.9, which is cos theta to be 0.9. Cos theta is S over P. Now for that we have to calculate our new S as well. We know the P, so cos theta is equal to P over Q, right? So what is new? P over S. So what now? Our new S is equal to P, which is 125 millisecond, 120 kilowatts. So 120 K divided by 0.9, which is 120 divided by 0.9 is 133, right? 133 kVA. That is our S, right? So to have that S, what is the required Q, right? So S squared is equal to P squared plus Q squared, right? So our new Q squared is equal to S squared minus P squared, which is 133 squared plus 120 squared equals to 133 square minus 120 square is equal to 3 point okay, 3289, right? 3289. So Q, our new Q is square root of that. Square root of that is 57.35 VAR. This is inductive, right? Inductive. Now what is QC? QC, what is the capacitor? The reactive power of the capacitor is the previous Q. What is previous Q? Previous Q is 160, right? 160 minus 57.35 VAR capacitive, right? So you add this minus, so there is 160 minus 57.35. You have to add a capacitor that has 102.65, approximately 103 VAR capacitive. So if you add a capacitor that has a capacitive reactive power of 102.65, approximately 103 reactive power, VAR capacitive reactive power, you actually bring the circuit to have 90% power factor, or zero power factor be 0.9, right? 0.9. So if you want to calculate the capacitance for that, what is C, right? Q is equal to CV, right? QV is equal to CV, or rather, if you use that, sorry. Q is equal to V squared over XC. So what is XC? XC is equal to V squared over Q. So V squared is 600 volts, it was, right? 600 volts squared, 600 squared divided by the apparent the capacitive reactive power 100, let's say 103. So that is 600 squared, 600 squared divided by 103, which is XL is 3495, right? Ohms, right? So what about C? XC is equal to 1 over omega C, or 1 over 2 pi FC, right? So F is equal to 50 Hertz, right? So therefore C is equal to 1 over 2 pi into 50 into XC, that is 3000 495. So that's 1 divided by, within brackets, 100 pi into 3495, which is 9 point, let's approximately 9 into 10 to the power minus 7, as I can see in my calculator, right? Farads, right? So if it is micro, it is 0.6, sorry, minus 6, so it's 0.9 microfarads, the capacitor that you want, right? So you need a 0.9 microfarads capacitor, right? Approximately 1 microfarad capacitor to achieve this, right? So that is how you do the calculations. I hope this calculation is correct, but you can double check it, right? So that is if you want to have a particular correction done. Now similar procedure can be used if you want to have 95%, or that is to make the power factor corrected to 0.95 or 0.8, whatever it is, right? So you can use those I mean the same procedure, but with a different power factor value, new power factor value, right? You have to actually draw the power triangle for the new power factor and find out the new Q, and the difference is the value of the capacitive reactive power that you need to add, right? So the moment that you add a capacitor that has a capacitive reactive power of 103, in this case your power factor is going to be improved to 0.9. Now you saw that it was actually at 0.6, right? Original power factor was 0.6. Now we are going to improve that to 0.9, right? Not to 1. If you want it to be improved to 1, then you have to add a capacitor that has a capacitive reactive power of 160 kVAr, right? So that's all for today. And if you have any issues, any doubts and things like that, you can always post us, or you can always contact us via WhatsApp. You are given the WhatsApp numbers of all the 5 members, right? So you can actually contact us via those, or we can talk about the doubts in the sessions that we are Zoom sessions that we are organizing, right? So until then, we will wind up the session at this point. Stay safe, stay home and stay safe, but don't forget to work. So you have to work as well, right? So we'll see you in the next lecture, right? We have one more lecture to go, that is on electromagnetic related stuff, that is inductors and things like that, or transformers and things like that. Till then we'll wind up the lecture at this point. See you all.